In this paper, we present a ray tracing approach to diffusion curves. Our approach is based on integrating the contribution of each curve at a shading point using stochastic ray tracing. Our method provides extended flexibility in achieving desired image effects. Specifically, we introduce generalized curve colors called shaders that allow for the seamless integration of diffusion curves with classic 2D graphics, including vector graphics, for example gradient fills, and raster graphics, for example patterns and textures. Here, curves are inserted and assigned shaders to produce the owl image. The video has been condensed for brevity. Notice how textures are added to the curves to produce a stylistic effect. Here, gradient shaders are used to create a star, the circular halo around the moon, and the purple highlights in the sky. Our algorithm works by assigning different shaders to the diffusion curves. We highlight a gradient shader, a texture shader, and a standard color shader. To render a pixel, we use stochastic ray tracing to shoot rays into the scene and integrate the results returned by the shaders at the hit points. Our method allows that each curve be defined with a flexible weighting function to customize the contribution of the curve. Here we show the user adjusting the relative weight of the gold curve in the center left of the image. The default weight is 1. Note that increasing or decreasing the weight results in changes in the curve's influence to the space between it and the blue curve on the right. We also show an example of enabling transparency. Here all curves are given an alpha value of 0.8. Here we show examples of different distance-based weighting functions. Note how changing the parameters affects the appearance of the image. We now show 2 additional examples of transparency. Here we show 2 animations created using our high-quality renderer. We do not notice any obvious sampling artifacts. During user interaction, we apply an adaptive sampling method to speed up rendering. Here we show only the pixels that are ray traced during user interaction and not those with interpolated values. After a period of user inactivity, our algorithm produces a high-quality rendering by ray tracing each pixel. We have found that the adaptive sampling produces reasonable quality during user interaction. This is the captured sketching session for the pipe image. The video has been condensed for brevity. Note the use of a radial vector fill to create a circular glow in the pipe's bowl, and textures added to create the wood grain and vary the reflection on the pipe's stem. A transparent backdrop is used here to allow the user to trace an existing image. Also note the quality of our adaptive sampling algorithm during user interaction. In this final example, curves are inserted and shaded to produce the bird image. This video has also been condensed for brevity. Note that the specular highlights in the bird's eyes are produced by a radial vector fills, and textures are added to the curves to produce a painted effect. Using our method, only a few curves are required to achieve this painterly effect. This concludes our video demo. Thank you for watching.